most important topic is finding zeros. What do we mean by finding zeros? Most of us in the school might have solved the quadratic equations like something like 3x squared plus x minus 4 equal to 0, right? Then that is the 3x squared, which can be written as 4x minus 3x minus 4 equal to 0. 3x taking px common, x minus 1 plus 4 common, x minus 1 equal to 0, or here 3x plus 4 x minus 1 equal to 0, x equal to minus 4 by 3 or 1. We have the formula minus b, the formula root b square minus 4ac by 2a for quadratic roots. For quadratic roots. So, unknowingly we would have all found zeros. Basically, the definition of zero, finding zero, what when we find a zero, we have y equal to fx, the function, for what values of x y becomes zero. That is the process of finding zeros. Meaning, what value if you give to x results in y being zero. So that is here, you see, if you in this equation, if you substitute 1 for x, what will it be? P into 1 squared plus 1 minus 4. That is nothing but b plus 4, 4 minus 4. Meaning, when you supplied 1 for x, it resulted in getting 0 for y. Right? So that is what is called finding the roots. Basically by vanishes. And there is a rule for all. This is a quadratic equation. This is quadratic, right? Linear equations. We can have linear equations, linear, quadratic, cubic. I don't even know what they call for the other things. So basically, we call these polynomial equations of single variable. And then, there is a what do you call this same thing? Finding zeros itself is, or otherwise you can call it finding solution. We all know about this solution all our lives, but we don't know about this finding zeros. That's only, people who deal with maths, humans, generally use this term finding zeros, and of course also the theoretical physicists and all who use higher engineering mathematics, higher concepts of mathematics. They use this concept, this name, finding zeros, whereas it is ordinarily known in schools and colleges as finding solution. What is find? How do you find solution? Of course, when f(x) equal to 0. Whatever function you create, equate that function to 0, then you will get the solution. So the polynomial roots, about polynomial roots, there is a theorem called fundamental theorem of algebra. What does it say? It says actually the fundamental theorem of algebra itself is called the of D'Alembert's theorem. The another name for fundamental theorem of algebra is D'Alembert's theorem, or even slash D'Alembert slash, sometimes goes D'Alembert slash Gauss theorem. Fundamental theorem. So what does it it states that single variant, as we have seen just now, single variant only x, single variant variable, or rather say it's the same word, I think, but single variant non-constant. What's important is non-constant single variant with complex polynomial, which rather read single non-constant variable polynomial with complex coefficients. Meaning, let's say single variable, we are saying sing x, c1x plus c2, x squared plus c3 x cubed, cm xn, like this, such a equation, such a let's say function, it has at least one complex. Complex coefficients. These are complex. C1, C2, C3, C4, Cn are where Cn are complex. So this such a single variant non constant polynomial with complex quotients has at least one complex root. Right? Only the quotients are complex here, not the function. Right? The quotients are complex, still it will have at least one uh, complex root. That's the DLMS theorem. Uh, Riemann's Zeta function. Riemann's zeta function is, let me just give me a second. Riemann's zeta function. He was basically, to begin with, he was playing with prime number. With those, he plotted with the prime numbers, let's say, like that, with he plotted these prime numbers like it comes like something like this. It like a step function. And later, um, he came up with one puzzle which holds even today, in the sense it is not solved even now. It's not solved. It has, in fact, um, it has $1 million, $1 million price. Let me see, $1 million. It's literally a $1 million question, $1 million puzzle, you can say. And Riemann came up with a function which is something like this. Like this. So the function itself is represented by the Greek letter zeta. Zeta S is equal to the summation of, from n equals 1 to infinity, 1 by infinity, 1 by yes. That is, this is the zeta function, zeta function, the famous zeta function. Or definitively, it means like the infinite series of, as you can see, it's a summation from n equals 1 to infinity of 1 by, sorry, sorry, n raised to s, n raised to s, So this is 1 by 1 raised to s plus 1 by 2 raised to s plus 1 by 3 raised to s and on 1 by n raised to sorry. I mean it goes on. It's infinite series. Infinite series. So the solution for this function nobody could find. So many were there, many tried it, but nobody succeeded in solving this equation. But I'm not very uh, sure how this can be written in a different form as zeta s is equal to 2 raised to plus pi plus minus 1 sine pi s by 2 20 minus s zeta. It's not zeta. Yes. It satisfies this equation. So when it takes the values of minus 2, negative, minus 4, minus 6, like that, negative even integers, if it takes those values, then this zeta function will become zero. When it confused with this phi or something, it is by way of writing 0. So let us make it as 0. 0. So that is the problem of the zeta function, which is not yet solved. Now, for that, what he proposed, Riemann's solution, what he proposed that though he did not find the exact solution itself, he said if you take he said it will have the zeros that we have, the zeros that we have somewhere here, somewhere for so when you substitute minus 2, minus 4, the value of the function when you substitute s with minus 2, minus 4, minus 6, like that you will have these zeros. These zeros are nothing but the intercepts of the x-axis. This x-axis is this one, and we call that the 0, and those zeros are called Riemann integers. Why? Because they are trivial. As I have given this equation in sine, the sine function disappears when the value of variable is minus 2, minus 4, minus 6, then that sine function disappears. So that's a solution. And So since it is very easy to get that solution, this substituting management sits and check. You can manually check it, right? So that those are called to. But apart from that, what he proposed is that there's a critical line, let's say, let us say, which is 1, 2, 3, 4. Um, okay, he said at half real value, he proposed, this is called critical line. He said the zeros, non-trivial zeros, lie on the line representing plus the real part is I plus IT, that's upon it. So the the line representing this, they will definitely lie on the line representing half. This is right 1.5. This is 1.5. That's all. 0.5. Between 0 and 1, at exactly 0.5, this line, critical line, lies. On the critical line on the non-zeros lie on the line representing this. This is itself is called critical. That was Raymond's hypothesis.